Hi, this is Jonathan Ventura, and I am an assistant professor at Cal Poly in San Luis Obispo, California. And I'm very excited to present to you our work entitled CasualStereo, Casual Capture of Stereo Panoramas with Spherical Structure-from-Motion. I'm presenting this work on behalf of myself and my collaborators at the University of Otago, Louis Baker, Stephen Mills, and Stefanie Zollmann. So a stereo panorama is an extension of the traditional panorama that provides a different image to each eye in the VR headset, thus providing stereoscopic depth cues. A stereo panorama cannot be captured by simply taking two panoramas next to each other. This would only provide stereo in one viewing direction. Instead, a stereo panorama provides stereo in all horizontal viewing directions, and you can see an example here as a red-blue anaglyph. So to capture a stereo panorama, we need to spin a camera in a perfect circle with the camera offset from the center while recording video. Image columns from the left and right side of the image are extracted and rearranged to form the left and right eye panoramas. Or alternatively, we can use a specialized multi-camera rig, such as the Google Jump, which has 16 cameras in a circle. And here we use view synthesis to fill in the missing viewpoints around the circle so that we can stitch together the panoramas. In this work, we are interested in enabling what we call casual capture of stereo panoramas, meaning that we can capture it with a single handheld camera, such as a smartphone. Because a person cannot reasonably capture a perfect circle of views with a handheld camera, because they'll necessarily wobble up and down, we use structure from motion to recover the actual viewpoints collected, and then apply view synthesis to render the perfect circle of viewpoints necessary to create the left and right eye panoramas. This process was pioneered by Ricart et al. In their 2013 paper on mega stereo, and later improved by Bertel et al. In their 2019 paper on mega parallax. So we have found that the use of general structure from motion tools is the major weakness in the casual stereo panorama pipeline. General SFM is not well suited to casual stereo panorama capture for several reasons. First, tools such as the state-of-the-art CoolMap system are slow, requiring 2 to 3 hours to process a scene of several hundred images. But more importantly, we found that general SFM tools are prone to failure when processing this type of video. The small baseline between frames makes initialization of the reconstruction difficult, and as you can see in the video example here, features are only in view of the camera for a short period of time, so it's difficult to find a pair of keyframes with sufficient baseline to initialize the reconstruction. Furthermore, the small baseline between views makes point triangulation and scale propagation unreliable. In this work, we evaluated an alternative to general structure from motion called spherical structure from motion, which I introduced in a 2016 paper at the ECCV conference. In spherical structure from motion, we assume that the camera moves at a fixed distance from the center of an imaginary sphere, with the view axis parallel to the normal of the sphere, so the camera is pointing outward from the sphere surface. In the case of casual stereo panorama capture, where the camera is held in an outstretched hand, we can imagine the user's shoulder would be the center point of the sphere. The camera's translation always is fixed to 0, 0, -1, so that there are only 3 degrees of freedom in the camera's pose, corresponding to the rotation of the camera. As the user spins the camera in a circle, we expect that the camera will necessarily wobble up and down, but these motions should be compatible with a spherical constraint, as long as the camera is always pointing out from the sphere. We won't allow movement in or out, left or right off of the sphere's surface, but such motions should be negligible if the user is being careful to capture a rough circle of viewpoints. In terms of SFM reliability, spherical SFM has several advantages. Because the translation is always fixed, we do not need to do scale propagation. Secondly, there's no ambiguity in 2-frame relative pose estimation, which is a problem in general SFM with small baselines when we try to decompose the essential matrix. So we saw that, for example, with CoolMap, when we processed our videos, it would sometimes choose an incorrect initialization of the first 2 keyframes, leading to a failure of the entire reconstruction. And in general, we were unable to reconstruct our video sequences with CoolMap. So our spherical SFM pipeline works as follows. First, we detect SIF features and then track them using pyramidal Lucas-Conade tracking, which provides sub-pixel refinement and thus better accuracy than tracking by detection. And that's important for these small baseline images. We robustly compute the spherical relative pose on the feature tracks and only accept a keyframe if we estimate its relative rotation to be greater than 1 degree from the previous keyframe. This allows us to adaptively subsample the input video to make processing faster, something that would be difficult with general SFM techniques. Finally, we perform loop closure on the beginning and ending frames of the video using SIF descriptor matching. Again, using the spherical relative pose. So to initialize the camera poses, we integrate the relative rotations that we estimated using L2 rotation averaging, and that provides a pose estimate for every camera at once, so we don't need to do an incremental reconstruction. Then we initialize the 3D point cloud using DLT triangulation with all the available observations. And finally, we perform robust bundle adjustment, keeping the camera translations fixed to maintain the spherical constraint. You can see here for the elf and forest sequence, the estimated camera pose is in red, and the point cloud is in blue. In our experiments, we noticed that if the spherical constraint was not used in bundle adjustment, the reconstruction would often diverge and result in failure. So we found that the spherical constraint was critical to robustly producing a reconstruction from such small baseline video. Finally, once we have estimated the pose of all the input keyframes, we use the mega parallax approach to do view synthesis. This approach uses optical flow between neighboring keyframes on the circle in order to inform the view synthesis. And from that, we render virtual viewpoints around a perfect circle to produce the final left and right eye panoramas. Here's an example with the elfin forest sequence. So on the top, you can see the red-blue anaglyph with a nicely stitched panorama. And on the bottom, you see a depth map that we've estimated using standard block matching stereo. And so you can see the tree branches are nicely estimated. You can see a lot of the depth of the near and far structures here. Here's another example of the children's garden sequence. And you can see some fine structures were estimated well on the left and right-hand sides. And that indicates that the camera poses were well estimated if we're able to get those depths. Here's a sequence taken under the Pismo Beach Pier, and you can see the pylons are well reconstructed. This was a difficult sequence because there was little texture to use for feature matching, and because of the sandy ground underneath us, it was kind of hard to do a level capture. And finally, here's one more example of the Owiho Courtyard at University of Otago, and this is actually where we did the user study that I'll discuss in just a minute. So for the evaluation, the first thing we looked at is the processing time, and we compared our system to previous systems based on the times reported in their papers. So Mega Stereo uses a single camera like we do, handheld capture. They process about 100 to 300 frames in about 2 to 3 hours, and that's really dominated by the structure-from-motion processing time. Systems like the Google Jump and similar use 16 camera rig, so they're not really for casual capture, and those work in about 4 to 20 minutes. A recent paper called Instant 3D processed a similar number of images in about 30 seconds, and that's because they use a stereo camera that helps them do the reconstruction faster because they have the depths to begin with. In our system, we use a single camera, so it's the most general, easiest capture process. We process 200 to 700 images in about 3 to 10 minutes, so we're actually faster than all of them except for Instant 3D. Okay, so we found that our system works well on the sequences that we captured, but we wanted to know the real-world applicability of our method. So we did that through a user study, and we wanted to answer 3 questions with our study. What level of training is required for users to produce stereo panoramas with our approach? Do the stereo panoramas produced by our approach appear convincing and natural to the participants? And how will participants perceive the parallax effect in our results? So we had two tasks in our user study. The first task was a capturing task. And here we had users capture a panorama first. With little instruction, we just told them to capture the panorama as they normally would. And then second, we gave them more detailed instructions to hold the phone level, outward, and make a complete circle to maximize the quality of the panorama. In the second task, we showed them a stereo panorama produced with our method, and then just a traditional mono panorama with the same image to both eyes in a VR headset. Our hypotheses were, one, that users will find the capturing process for capturing stereo panoramas similar in usability to standard panorama captures, and two, that users will be more likely to perceive a stereoscopic effect when watching casual stereo panoramas in a VR headset compared to a standard mono panorama. So we had 12 participants recruited from the undergraduate and graduate student pool at University of Otago, 3 female and 9 male, ages from 21 to 31. And all the participants either had experience with capturing panoramas or knew about the process. So first, we had 12 participants, and so each one collected 2 videos, one with little instruction and one with detailed instruction. And out of those 24 videos, 22 were successfully reconstructed by our method. Of the 2 that didn't work, one had focus problems, so it didn't really focus correctly, and the other one, the participant didn't close the circle, so we didn't get a good loop closure. On the questionnaires, participants did not find the capturing process significantly better or worse, comparing the little instructions to detailed instructions. So this confirms hypothesis 1, that they wouldn't find the process any different from a normal stereo panorama capture. And second, participants' perception of the stereoscopic effect was significantly greater with stereo versus mono panoramas. So this confirms hypothesis 2, that we are able to produce high-quality stereo panoramas that give a good parallax effect. Here are some examples of panoramas reconstructed from the participants' video. So on the top, you see one with little instruction, just normal panorama capture. And on the bottom, the detailed instruction where they were instructed to be very careful about the process. And you can see both seem to be reconstructed well with good parallax of the nearby objects. So to conclude, we found that spherical structure-from-motion enables robust, effective, casual stereo panorama creation with a single handheld camera. It's substantially faster and more robust than general SFM for these kinds of videos. And through our user study, we confirmed that the method works reliably when users capture a panorama normally, just as they normally would when capturing a normal panorama. Finally, I just wanted to note, we did find sometimes that at the loop closure point, the camera might be a little bit higher or lower than it was at the beginning, and this might cause a seam in the panorama, which you can hopefully see here on the right in the detailed view. And so that's something where we wondered if we might be able to relax the spherical constraint to allow some deviation from that hard constraint without breaking the reconstruction. So there might be some way to have a relaxed constraint to still have these benefits, but get a bit more accurate reconstructions in these challenging sequences. So that's an idea for future work. With that, I'd like to thank you for listening. I would like to acknowledge the National Science Foundation and the New Zealand Marsden Council for their support of this project, and just note that code is available on GitHub, and you can also see some examples of our panoramas in WebVR through a headset. Thank you.